All right, hello. I'm going to tell you about a new feature in CoCalc called Cloud Filesystems. Basically, they provide a full file system that works pretty fast on all of your compute servers at the same time with relatively low latency, so that you can use Git and quickly read through 50,000 data files or whatever. And the really cool thing is you can mount this file system on machines on multiple continents simultaneously and fully use it. So I'm just going to demo it for you. This is a great place or a great file system in which to store long-term data. First you write your data to the file system, you can read it back quickly, you can read it from other machines, you can warm it up to a local cache, as I'll demonstrate. And if you let your data just sit there over time, then after a while it gets cheaper and cheaper and cheaper. It starts out costing about 3 cents per gigabyte per month, but it goes down over time. After a year, if you're not accessing a particular block in a file, it goes down to as little as a couple of dollars per terabyte. It's really, really incredible. So anyways, let me get going and show you a demo. So first, let me check out my projects. I have a project called Demo, and here's my goal. I'm going to create 2 compute servers. Compute server 1, and compute server 1, I will place it geographically on the West Coast, so US West 1. So it's in Oregon, and let's just use the default N2D, and I'll just leave everything else exactly the default. Okay, so I've now created compute server 1 in Oregon. I'll create a second compute server 2 on the far, far away. So this one's going to be in Europe. We'll put it in Italy. Okay, and let's start that one going. Okay, so now we have these 2 compute servers that are far away from each other. And what we like is to have a pretty fast file system where changes are instantly, almost instantly, obviously not instantly, visible between the 2. With no manual synchronization process needed. And what we're going to use is called a Cloud File System. So just click on this tab, Cloud File Systems, and let's create a Cloud File System. We have to choose the physical location in which the data will be stored, and I'm going to choose US West 1. So it's going to be close to my server on the West Coast. The idea is that mainly I'm going to be using the server on the West Coast, and that's where I'm going to put the file system. But sometimes I want to use it from Europe or Asia or somewhere else just because I get a good deal on compute resources there or for some other reason. So let me click Create, and there we are. We now have our new file system. It's mounted at cloud, and let me kind of shrink this a little so you can better see some of these options. So it's mounted at ~cloud, that's the mount point, and maybe I'll change the title from untitled to demo, and I'll choose a more exciting color like that red there. Okay, let's check on the status of our compute servers. So while I was creating the cloud file system, both compute servers booted up and they're fully running. Now let's make a terminal so that we can get a command line on each of these compute servers. So I'll just click on Linux terminal. And I'm going to switch this terminal so it's on compute server 1. And then I'm going to split the terminal and make it so the terminal on the right is on compute server 2. And I just realized that it might be hard to see what I'm typing on the right because of my little video thing here, so I'll do that. So now they're above each other. Okay. Now, first let's type df to see what file systems we have. And notice there's a new file system called Home User Cloud. That's the cloud file system I just made. So let's look in there, and there it is. Notice that this file system is accessible from both of the servers. The one on the bottom, which I called 2, but let me click here and rename it to Italy. The one that's in Italy, it's equally accessible from both of them. So let's do something just to play around with these. So I'll do time get clone and I'll grab the source code of CoCalc. And this should take about a minute. It has to download about 600 megabytes of data and then extract it. And while it's doing that, I'm just going to open another terminal on my compute server that's in Oregon and do a few things. So first, if I do df-h/, you'll see that 7.2 gigabytes of data are used on this compute server. This is the local root file system of the compute server. If you do df-h in the home directory, there's a file system there that's 13 gigs. That reflects my shared resources project, just like the part of the normal CoCalc cluster. And then finally, as we know from before, the Cloud File System that I just created, that has a petabyte free, because Cloud File Systems basically have an unlimited amount of space in which to write files. And so far we've written nearly 519 megabytes. And if you look at the file system from Europe, it looks the same. You can see that it's getting the CoCalc source code. So let's let it finish. Also, if I type CoCalc -h, there's a new command called CoCalc, and one of the subcommands is CloudFS, and then that has a subcommand stats, and that'll tell us the stats for the current directory. So let me go into the cloud directory, and it tells us if it's reading or writing to the remote file system. There's really nothing going on right now though. Okay, now let's try to use our new file system. So I'll do git log. Oh, I have to change into the file system that has, or into the directory that has CoCalc. So type git log, and there it is. That's the log of our files. And we can do find dot, so you can see all the files. There's 4,700, and this is very fast. So this cloud file system, it's based on JuiceFS, which is itself based on Redis with multi-master replication as implemented in KeyDB, and the architecture, how it actually works, is it uses a Redis in-memory database to keep the metadata about the file system in sync, and it stores the long-term blocks of all the files in Google Cloud Storage. The net result is that you get very cheap long-term storage, efficient access to your data from all over the world, and fast metadata. So the file system can quickly do things like directory listings. And if we go down here and then say make a little change, so this is in Europe, I'm opening the file, make a little change, save the change, and then go back here and look at it, we can see that the change has been made. And then I could do like get diff here and see the difference. So I'm just going back and forth between the US and between the west coast of Europe and Italy, and I have this network file system. But it's really nothing like what you get with NFS, because the latency is just a lot less. There's no round trip back and forth to Italy every time you want to do a write to a file. It's much faster than that. Otherwise, just extracting CoCalc would be pretty slow. It's also nothing like doing a fuse amount of Google Cloud Storage directly, because that doesn't have proper POSIX semantics, whereas this file system satisfies the full POSIX test suite. So you genuinely can use it like a normal file system from your applications. So in Europe, and this one over here, though it's reasonably fast, like all the metadata is instant, just like before, and we can certainly read individual files quickly, there's one thing that will be pretty slow, which is if we want to read in bulk all of the data, like for example, we want to do a git clone of the CoCalc directory, which involves reading all 500 or 550 megabytes of data, or if we want to tar it up or back it up or something, that can be fairly slow. So if you have a specific directory where you want to do a lot of work with that directory, you can very efficiently in parallel download all the underlying blocks for that data to a local cache, assuming you have enough disk space. And then what happens is the data is read from that local cache, and it's just a lot faster. So all you have to do is type CoCalc warmup when you're in the appropriate directory, and it will download all of the data for that directory so that it's usable locally. So there's one catch with this cloud file system in that you do have to pay some bandwidth fees. So I'm going to have to pay a little bit because I'm downloading all this data which I uploaded to Google Cloud Storage on the West Coast. I'm now downloading it to a Google data center in Italy, and Google charges some amount of money for that. It's going to be about 5 or 6 cents. And by the way billing works for the cloud file system is we charge you a 30% markup over exactly what Google charges us. Unfortunately, Google doesn't tell us what they're going to charge us until 2 days after the charges are incurred. I have instrumented for the file system stuff that gives an estimate for the cost so far. And so you can see here the estimated cost so far is 6 cents, which pretty much matches up with what I just mentioned. And so you can see little plots using Plotly and what you've done and why the cost is what it cost. But the actual bill and the exact actual cost doesn't come for 2 days. In any case, we now have the CoCalc file system in both places. We can fully use it in both places. And this is across the globe, but it feels super fast, like a local file system in both places simultaneously. Obviously, it's impossible for it to literally be fast and simultaneously accessible and consistent. So there's the speed of light, there's time that the replication takes. So if you write something, in Europe and then try to read it instantly in Oregon, it's not going to be ready yet and there'll be this delay. Also, if you try to write two things at basically the same time, there's a last write wins semantics. Okay. So that's the file system. We're using it from both places. What else should I show you? There's an integrated backup system. So if I do CoCalc, let's see if I do, if I do CoCalc backup, let's see what happens. What this will do is it creates a repo using Git, and then it copies all of the data anywhere in your cloud file system into that repo. And it does this once, and then successively, as you edit and add new files and make changes, it just copies over the changes. And the backup, which is just integrated, all you have to do is type CoCalc backup. The backup, it's deduplicated and compressed. And that's across everything that you're backing up. So as you do additional backups, it's very efficient in terms of space usage. You might be worried that the Google Cloud Storage bucket that hosts your file system is the exact same bucket that I just did the backup to. And that would be a very reasonable concern. Fortunately, you can just create another bucket if you want. Just go here. You can make a whole bunch of cloud file systems. So let's make another one and just call it backup. And I'll mount it in the location backup. And I didn't really show you this, but in addition to all these locations, there are some advanced settings. You can choose multi-region, and that will let you make a cloud file system that covers the entire United States, or it covers all of Europe or all of Asia. And what that means is that upload and download is generally much more efficient for any compute server located in the corresponding multi-region. And also the pricing is a little bit different. So the cost to upload in the same region is free, but then once you upload, there's an additional cost for the data to get replicated across that region. So the pricing is just a little bit different. In any case, let's just set this one, the backup, to again be in US West. But instead of US West 1, let's make it US West, 4. Maybe a little more safety because we want the backup. If US West 1 is completely down, we want our backup to still be accessible. There's also a bunch of advanced settings. So you can type a phrase here. Please don't delete this critical backup, future self. And all this means is that when you do go to delete your cloud storage bucket later, if you do, you'll have to type this passphrase. You'll see it listed right there for you. You don't have to copy it down anywhere. It's entirely just to add a little tiny bit of friction to avoid accidentally deleting your data. That said, it's extremely straightforward to delete a cloud file system after you create one. There are a whole bunch of different, we support all the different Google Cloud storage classes, so you can store all of your data standard, nearline, cold line, archive, auto class transitioning down to standard or nearline, or auto class transitioning all the way down to archive, which is the default and makes a lot of sense for the use case that we have here. With backups, by the way, they're already compressed, so if everything you're going to store is backed up, there's no need to turn on compression. Otherwise, though, cloud file systems are by default LZ4 compressed. It uses just a little bit of CPU and can easily reduce your data cost by a half. It reduces the bandwidth cost and it reduces the app storage cost. It's just completely transparent. So you have that as well. Also, there's a block size parameter, and in the way costing works with Google Cloud Storage, each block that you upload ends up costing a certain amount, maybe like 1/1000th of a penny. But if you upload hundreds of thousands of files, they're going to be composed of a large number of blocks, and so using a large block size is really advantageous. And there's even some technical mount options that you can configure here. Anyways, let's create our file system. So click Create Cloud File System. There it is. It takes about 10 or 15 seconds from when you create a file system until it's mounted. So it's not quite mounted yet. Not quite mounted yet. And there it is. So it's now available as backup. And again, these file systems, they get mounted everywhere on all of your compute servers. Note though, if you look at the normal compute, the shared resources, so not on a compute server, then it doesn't see the cloud file system yet. So notice there's this directory just because we're editing files there, but if you do df-h, you'll see that there's nothing mounted related to the cloud file system. This is not the 1 petabyte of data, and there's no backup thing. It's just not available on the shared resources. It's only available in the compute server. That should change in the future though. Okay, so let's go back here, and I'm just going to make a backup again, but I'm going to make the target be this new backup disk, this new backup file system. So all you have to do is do CoCalc backup from the file system that you want to back up, and you give the target where you want the backup to go, and it will back up there. And so now this backup file system, instead of being empty, it's filling up with data. And you can make one cloud file system backup a whole bunch of data from all over the place to that file system. And it's deduplicated and compressed across all of that. So it's just nice to have an easy way to have backups created and browsable this way. And every time you make a backup, you can just browse it from your from the .backups directory. And there it is. And you can look inside and see your files. See? And you can also delete old backups and so on. The backup system under the hood uses BUP, which is based on Git. And it's a very powerful and reliable backup system. Okay, is there anything else to show you? Well, I mean, the main point, the thing you're going to often do with a compute server with a cloud file system is maybe you'll want to do something with a Jupyter notebook. Okay, let's run a notebook on our compute server. Make sure to refresh the kernel list. Okay, choose the Python kernel. All right, so we can see that the CoCalc directory is there. And let's make another Jupyter kernel, or another Jupyter notebook that is running in Italy. I'll just call it Italy. Set it to run in Italy. Okay, and there it is. And also do that just to see it is running. And I don't know, just do something silly. Let's open a file in the CoCalc directory and display it. same thing over here. And the idea is we're using Jupyter notebooks to operate on the same file system, but from all over. So you can see how that would be very useful. And you're keeping your Jupyter notebooks in a clean, sensible way. They're all very efficiently accessible within one file system across a large number of compute servers. If you want to write out a large amount of data, a terabyte of data, whatever, that's perfectly fine. Warning, this file system is great for a large amount of data, but there are limits on the number of distinct files that you'd want to save in one file system. Like, you would definitely want to keep it below about 5 million distinct files. If you have a huge number of files, it's better to archive them together into one bigger file, or create separate file systems. The reason is that the entire directory tree is always stored in memory all at once. Okay, so I've now shown you how to create 2 different cloud file systems and use them from 2 different compute servers on opposite ends of the world, or at least of the northern hemisphere. So now the last thing I'm going to do is just close these Jupyter notebooks, and then I will delete the cloud file systems I created and also the compute servers. So in terms of deleting the cloud file systems, first we have to unmount them, which is due by clicking, and I'll unmount the other one. Notice the unmounting is a little funny because I'm actually using the directory here. So it's kind of like trying to, it's not very happy that I'm unmounting it while I'm in that directory. And obviously I can't do ls on a directory that I've just unmounted. So, but it's fine because I'm about to delete these cloud file systems. So I've now unmounted them, then I click delete file system. And I have to type that message I mentioned, or at least I can copy paste it. And then it lets me delete it. And there it goes. And this other one, I'm going to delete this one as well. The default is just delete. Okay, the cloud file systems are being completely wiped from existence. Interesting note, behind the scenes, this uses a trick with something called the storage transfer service to very, very efficiently delete the underlying Google Cloud Storage bucket, even if it has millions and millions of files in it. It's really the optimal way of doing the deletion. So that's kind of nice to know. Okay, and then the compute servers, I will also delete those. And I'm clicking deprovision because I want to completely delete the compute server, its underlying file system and so on, since I don't need them after this. And what deprovision does is it leaves the configuration of the compute server around, like the name of it and the title, so you can create it again if you want, but there's no cost at all. Okay, so these will be deprovisioned, and then all charges stop. If you look at the upgrades panel, you can see all the purchases that we had during this discussion. So there was a little bit of network data. There's a little bit of cost for running these compute servers, about a penny for each one over here. So you spend about 2 cents on the compute servers, and then the actual cloud storage, well, the cost won't actually be listed here for 2 days, but it was probably about 5 to 10 cents total overall for everything we did. And most of that cost was just the bandwidth to probably download to Europe from the US. And then there's some cost for all the individual files that we created. Okay, so now we're almost done cleaning everything up. There's a couple of files laying around, so let's just delete those. Boom. And now everything's cleaned up and we're done. Okay, thanks a lot for watching this demo. I hope you give Cloud File Systems a try. If you have questions about using them at scale, or anything about how they work, or should they work for what you're doing, just reach out. Email help@cocalc.com, click on the help button, and we can chat. Thank you. Bye.